Welcome to another tutor short provided by the Educational Support Services Department of Lehigh Carbon Community College in Schnecksville, Pennsylvania, which is just outside of Allentown. These videos review key learnings for the science courses provided here at LCCC. And please remember that the Educational Support Services Department does provide walk-in tutoring 5 days a week. This video will review the terms you see up above here: elements, atoms, ions, and isotopes. I'm going to run through this pretty fast since there's a lot to show, but feel free obviously to review this video over again and stop it as you need to grasp the ideas that I'm presenting. We're going to start with the term elements, and elements are the pure substances from which all other things are built. And you've heard about them. Copper, aluminum, oxygen, nitrogen, iron are examples of elements. And one distinction to make, I use the example of water. Water isn't an element. If you remember, water is H2O. It's actually made up of the elements of hydrogen and oxygen. And you put them together in this form, you make a compound called water. Water itself is not an element. It's made up of elements, and water is a compound. So that's a distinction you need to understand. Now, if you take a pure compound, and let's use an example of iron. People can visualize, hopefully, a block of iron. That is an element, a pure compound. It's just iron in that block of metal that you have. If you break that block of metal down to the smallest piece, okay, we say here the smallest particle that still retains the characteristics of the element, then you're down to an atom. So that's what an atom represents. And if you, again, you probably are familiar that when we talk an atom, so an atom of iron, when we talk atoms, typically talk about a nucleus, and surrounding the nucleus are where the electrons are flying around, and inside the nucleus are your protons and your neutrons. So it's very classically represented sort of like a moon with the nucleus, our moon or the earth, center, and flying around it is the moon, which is the electrons flying around that central nucleus. You can't, if you break an atom down, meaning you take that iron atom that looks something like this representation here, and you break out the electrons and take them off, put them somewhere else, and you take out the protons over here. Well, now you've broken it up smaller, but now a proton by itself doesn't act like iron, and an electron by itself won't act like iron. It's only when it's in this configuration here that it represents iron, that it behaves like an iron atom. So this is the smallest particle you can get down to, this atom that has the electrons, protons, and neutrons in such a way to make up that element. In this case, we're talking about iron. So classically now we've got down from elements to atoms, and we've talked about the particles that make up the atoms, and I want to go over those quickly here. We mentioned protons. They're in the nucleus. They're represented with a p, small p, with a superscript of a plus. That represents that protons have a plus charge, a +1. So a proton has a +1 charge. It weighs 1 AMU. AMU stands for atomic mass unit. And if you can imagine, that's a very, very tiny mass. When you can compare it to pounds or grams, kilograms, an AMU is very, very small. And as we said, protons are in the nucleus. The neutrons, they're also in the nucleus. They're represented by a small n with a superscript of a 0. That 0 represents there is no charge. It's electrically neutral. It's not plus or minus. It's just a neutral particle in there. It also weighs about 1 AMU, the same as a proton, and resides in the nucleus like the protons do. And then the electrons, the final subatomic particle we're going to talk about here, it's represented by a small e with a superscript of a minus sign. That represents that it has a -1 charge. It is essentially weightless. It's more than 1,000 times less massive than either a proton or neutron. So when we talk about how much does an atom weigh, we typically just ignore the weight of the electrons because they're so small compared to the weight of the protons and neutrons. And as we said, they reside in a larger space. They're zooming around the nucleus. One other thing about these charges, the +1 charge for the proton and the -1 charge for the electrons, the +1 and -1 is also representative of the strength of the magnetism or the charge. So these have the same strength, only in opposite directions. A proton is a +1 and an electron is a -1. So if you have, say, an atom that has, say, 5 protons and 5 electrons, because each one is the electrons are each -1, the protons are +1. Total, you have a total of 5 plus charges and 5 negative. So together, they're balanced, they're neutral. The overall charge of that particle, if you had these two together, would be 0 because they cancel each other out. So that 1 also represents a strength or sort of a volume of charge. So we're now going to look at the bottom here. How does a chemist represent these protons, neutrons, electrons? Because sometimes they change. So typically, I'll show over here. Typically, you'll see a chemist write something like that. Mg is for magnesium. That's the symbol for magnesium, Mg. And you'll see these numbers around it: a 12 down here, 24 up here, and a 12 over here. So what they represent, this 12 on the left-hand side as a subscript down below, that represents the number of protons that atom has. And that's also called the atomic number. So the number of protons that an atom has is the atomic number, and they show it down here on the lower left. The number on the upper left, the 24 over here, that's the atomic mass in AMUs, atomic mass units, and it's the sum of the protons and the neutrons. As we said before, each one weighs almost exactly 1. And the electrons you can ignore. So you just add the number of protons and neutrons together and you get your atomic mass in AMUs. In this case, over here we said 24. So the atomic mass for this atom would be 24 AMUs. And if you want to know how many neutrons is in this atom, you know that there's 12 protons. So you know this number here is 12. So if the total is 24, then there must be 12 neutrons. 12 and 12 together is 24, and that's what you have over here. So that's that representation. And then the final number is the number on the right as a superscript. In this case, it's 12. That's the number of electrons. And so this particular atom has got 12 protons. It's got a total of 24 protons and neutrons, which leads you to know that there's 12 of the neutrons, and then it has 12 electrons over here. So that's how you can represent an atom, or how a chemist would represent an atom that they're talking about. Now, so we've talked, quickly about a bunch of stuff here, but as far as our beginning, we've done elements and atoms, and we've thrown in some of these subatomic particles. But now let's talk about, well, what are ions and isotopes? And that's when you vary what an atom looks like. And so go over to this next page. I represented again the magnesium and what the subscripts and superscripts are again. Only now you'll notice over here I have the word element. Remember before we said this was the atomic number. I'll use that sign there for number. The atomic number. Here I say element. The reason I put the word element there is if you change the number of protons in an atom, you have now changed the element. So protons identify the element. And let's do it quickly over here. If I have 12 protons, I have magnesium. Magnesium always has 12 protons, never any more or any less. If you change this 11 and you say I got an atom with 11 on there, 11 protons, you no longer have magnesium. The element changes. If you look at a periodic table over here, magnesium is right here. The atomic number is 12, the upper number here in the box. If that's the number of protons. If you change it, somehow you took away one proton from that atom of magnesium. Now you have 11 protons in the nucleus. You do not have magnesium anymore. You've changed the element. It's now a sodium atom. And if you added a proton into that atom some way, now you have 13 protons. You no longer have magnesium atom. You have an aluminum atom. So the proton tells you what element you have. Now we go back. So we know the protons tell you the element. Now let's look at isotopes. Isotope, remember, is over before we said if you add the protons and neutrons together, that's your atomic mass. Remember in AMUs, atomic mass units. You just add the two together, tells you about the amount of atomic mass. Well, if you change the number of neutrons in an atom, you're going to form different isotopes. So we use the term isotope to represent atoms that have varying amount of neutrons. So we found in nature, magnesium in nature has 3 different isotopes. The most prevalent one is with 12 neutrons, and that's the one I represented here. You have 12 protons and 12 neutrons. You have a total of 24. That's the most common one in nature. But you will find some magnesium with 13 neutrons and with 14 neutrons. Now remember again, if I change the protons, I don't have magnesium anymore. But if I change the neutrons, I can still have magnesium. And in nature, we found that sometimes you'll have either 12, 13, or 14. And so if you remember, you add them up. You add the protons and neutrons together, get your atomic mass. So I clean this up a bit here. Let's go over to our periodic table. And you'll see here magnesium, the atomic mass, is the number below the symbol. And for magnesium, it's 24.31 AMUs. That means if you add up the protons and neutrons of a typical block of magnesium, or an atom of a block of magnesium atom, you'll get, on average, about 24.31 AMU. What that means is you have a whole bunch of magnesium with 24 atomic mass, which is the protons and neutrons. That means the number of neutrons is 12. The 25 magnesium, where you have 13 neutrons, it would weigh a little bit more. It's going to weigh 25 AMUs instead of 24. And 26 AMU is going to be the magnesium that has 14 neutrons in it. And so in nature, you're a little bit higher than 24. So most of the time, a majority of the time, you have magnesium 24 in that block of magnesium. But you're going to have a little bit of 25s and 26s in there too. And that's what raises the average weight of magnesium to be a little bit heavier than 24. So by looking at this number down below and considering the number of protons plus neutrons, you can get an idea of which isotope is more common in nature. And if we go back here, I'll clean this up. If we go back, as we said here, with the different number of neutrons, a chemist would represent magnesium-24. That tells you that's magnesium with a 24 atomic mass. This is magnesium with 25 and magnesium with 26. All three of these are isotopes. This is an isotope, and it's the most prevalent one in nature. But there's also a magnesium-25 isotope and a magnesium-26 found in nature. Only the most prevalent one is magnesium-24. So that's how they'll represent the different isotopes of magnesium. Now finally, we've dealt with protons, changing neutrons, and what that does. Now the final thing is changing electrons. Now in nature, elements are going to have an equal number of protons and electrons. They are going to be electrically neutral. And to think about that, again we go back to this sign. If we had 5 protons in your nucleus and 5 electrons flying around, it's called electrically neutral. It balances completely, and that's how nature likes to behave. It wants to be neutral. If it's a positive or negative charge, it's not neutral. It's not balanced, and it tends to react with other compounds around it. So in nature, you'll find things stable and in neutral condition, and so you normally will always have the same number of protons and the same number of electrons so that they're balanced. And so when you look here at the periodic table and we take chromium right here, chromium has 24 protons, so in nature you'll always find it with 24 electrons. So it'll be electrically balanced. Take any other magnesium, it's going to have 12 electrons. So you look at the protons, and that tells you how many electrons you have. Naturally in nature, you'll get a nice balanced atom. If you change, somehow you physically go in and strip away an electron, or you add an electron to an atom, now you're going to make an ion. Now you're no longer balanced. We call atoms that are not balanced ions. And the way we'll show it when we're talking about ions, if you just show Mg without anything near it, that's neutral. If you show an Mg with a 1 minus, is the way they like to represent it. That's saying it's got a -1 charge. It has an extra electron, because electrons are negative. So 1 electron would be a -1. If it had 2 extra electrons, it would be a 2 minus. This is a superscript up above the as a script. So if it had 2 electrons, it'd be -2. If it had 2 less electrons than normal, it would be a 2 plus, because it lost 2 negative electrons. And if you remember we did before, normal magnesium has 12 electrons. So this ion has only got 11 electrons. Oh, sorry, it's an added electron. It's got an extra electron because it's -1. So this has 13 electrons. If this is 2 minus, it's got 2 extra electrons. That has 14. This one has 2 less than the normal 12, so this has 10 electrons. So ions are represented by showing this -1, -2, +2 on the symbol of the material. And one final nuance that chemists would like to use is if it's an ion that has a negative overall charge, a -1 like this one here, magnesium -1, you call that an anion, and if it's a positive charge, you call it a cation. So an ion up here, ions, you either have positive or negative. If they're positive, you call them a cation. If it's negative, you call it an anion. So that's one other level of nomenclature you need to understand when we talk about ions. So that reviews all the different ways that you can represent an element and its atoms and vary the amount of protons, neutrons, and electrons and get the different isotopes and ions. Thank you.